Hello, calculus students, and welcome to today's lesson on integrals. Now, in the previous lectures, we've discussed all the basic integrals as you can see on this table to the left, where we have rules about integrals with constants of powers, where we have the integral of du is just u, integral of a constant is a times u plus c. We have all the trigonometric ones as stated here. We also know some of the inverse trigonometry like arcsine, arctangent, and arcsecant. In the following week, what we learned about partial fractions, which involve rational functions in which we can describe the factors that are in the denominator as terms that are in fractions that are added together. Today's lesson will involve the next lesson of this chapter, 7.2, which will be integration by parts. And the idea is it's closely related to the product rule. Now we know the product rule, if we have u times v and we were to take the derivative of this, then we would have u prime v plus v prime u. And what we can do instead is we could rewrite this as duv is equal to du times v plus dv times u. And we wish to write this in terms of an integral such that what we have as a result is that the product uv is equal to the integral of v du plus the integral of u dv. And for our purposes, we wish to solve for this particular integral, the integral of u dv, which due to algebra, we will get u dot v minus the integral of v du. So starting with this, to get us started, let's look at our first trigonometric example in which we have the integral of x times cosine of x dx. So the idea here is this. If we have the integral of u dv is equal to u dot v minus the integral of v du, we have to select a u term and we have to select a dv term. Now the dv term is always going to include the dx. And so the idea here is you wish to select u that will essentially disappear as you take successive derivatives of it. And in this case, that's going to be this x, because we know du is going to just be equal to dx, and therefore we no longer have to deal with that term. And you'll see why we do this. The only thing that's going to be left over is this cosine dx, in which case the dv is going to be cosine dx in its entirety. And if we were to integrate both of these, then v itself is going to equal sine of x. Now let's see what happens as a result. We've identified what are the terms of u and dv. We found essentially du and v, and now we will substitute in these u and v values into this term, which gives us x times sine of x. And now we're going to subtract this with our newfound term of v, which is going to be sine of x, coupled with dx. And now what we can see is that we are representing this integral that we didn't know what to do, product of x and cosine of x, which now when we take the integral, it should equal x sine of x, and a secondary integral, which is now easier to solve because we intelligently substituted the u into x. And so therefore, what is the integral of negative sine? That's going to be positive cosine. So as a result, this should be x sine of x plus cosine of x plus c is going to be equal to the integral of x cosine of x dx. Well, what happens if we have another integral like x times sine of x dx? Same rule is going to apply, and let me partition this so that we have u is equal to x, which tells you that du is going to be dx. Therefore, dv has to be the remaining term, which is going to be sine of x dx, and therefore v is going to be negative cosine of x dx. And when we do our substitution of u and v, product of uv is going to be negative x cosine of x dx. And we will then have to subtract the integral of v, which is also a negative cosine of x. And so we'll see that we're going to do a negative times negative, which is going to be positive, times du, which is this dx. And therefore, this becomes negative x cosine of x. Notice that I have not yet taken the integral yet. All I've done is just distribute the negative cosine of x dx. And we know that the integral of cosine of x is going to be sine of x plus c. Another type of integration by parts problem is the integral of x times e to the x dx. And when we do our u dv substitution, we set u equal to x, in which du is going to be equal to dx, followed by dv equaling the remaining e to the x dx, and e to the x being such an easy number is going to be e to the x. So we then expect this to be equal to u dot v minus the integral of v du. And for our parameters, we have the following. We have x e to the x minus the integral of e to the x dx. And this becomes x e to the x minus e to the x plus c. Another variant of this problem would be x times e to the negative x dx. So all what we've done is we've replaced whatever the coefficient is in front of the exponent of the exponential. Same rule applies. We set u equal to x. We set du equal to dx. dv is going to be e to the negative x dx. And now we have to be careful. The integral of e to the negative x will be v, which is negative e to the negative x. And so as a result, we have the following. We have negative x e to the negative x minus the integral of negative e to the negative x dx. And first what I'm going to do is distribute this negative so that we rewrite it as negative x e to the negative x plus the integral of e to the negative x dx. And now taking this integral, I get negative x e to the negative x minus e to the negative x plus c as my answer. So far, based off the past examples, you may think that whenever we have a product, it's always a good idea to set u equal to whatever the non-cosine, non-exponential form. But in fact, there's actually a particular pattern, and this pattern is called ILATE. And this pattern tells you what do you set precedence to set u equal to, where the I sets inverse trig, the L sets for logarithms, the A is algebraic, the T is trigonometric, and the e is exponential. So far we've seen the integral of x cosine of x dx, in which case we had the product of an algebraic with the trigonometric, which tells us that our precedence of u must be substituted with the algebraic, hence we used u is equal to x. In our second example, we had x times e to the negative x dx, in which we have a product of an algebraic with an exponential, and once again we're forced to choose the algebraic term, the x to whatever power, as the u substitution. So we will now take the opportunity to do the integral of the natural log of x dx. Now it might be quite surprising that we don't quite necessarily see a product, but let me remind you that anytime you only see one term, you can always imagine the denominator as being 1, or you could think of it as being multiplied to 1. So in this case, what we really have is we have an algebraic and a logarithm. And this is the first instance in which we see that we now have to set precedence to the non-algebraic term. We set u equal to the natural log of x. And when we do this, we take the derivative, we get du is equal to 1 over x dx, followed by doing dv of the algebraic, which is just going to be 1 dx. Quite interesting. And this results in the v being equal to x. So let's see what happens when we do our uv minus the integral of v du. And we get the following. We get x natural log of x minus the integral of x times 1 over x dx. And it turns out that the product of x and 1 over x just is equal to 1. So therefore we have x ln of x minus the integral of dx. And the result is going to be x ln of x minus x plus c. Try it out. Take the derivative of this term, see if you get the natural log of x. Let's do another example in which we take the integral of the natural log of x, but this whole thing is going to be squared dx. And note, typically whenever you're taking the integral of a natural log without a smart u substitution, this is what we need to do. So we set u equal to the natural log of x squared, and du is going to be equal to 2 times the natural log of x times the derivative of the base, which is going to be 1 over x dx. And we have dv, which is equal to 1, and we're going to have dx, and therefore v is just going to be x. So now when we do our integration by parts, we get x times the natural log of x squared minus the integral of 2 times natural log of x times 1 over x times dx, in which the x natural log of x, so this x is going to be the v, this is going to be the du, and we see that this cancels out and we're left with x times natural log of x squared minus 2 times the integral of natural log of x dx. And what you'll notice is that the integral of natural log of x is something that we solved from the previous problem, which should equal x ln of x minus x plus c. So therefore, I know that this is going to be x times natural log of x squared minus 2 times x ln of x minus x, and we'll just put a plus c on the outside. One more examples with logarithm would be the fact, what if we have the integral of x squared times the natural log of x dx? So now we're tempted to do the u substitution with the algebraic, but remember this is an algebraic logarithmic, so we have to set u equal to the natural log of x and which sets du is equal to 1 over x dx. And what we see is that when we set dv equal to x squared dx, the resulting v is going to be 1/3 x cubed. When we now do u dot v, that's going to give us 1/3 x cubed times the natural log of x. We will now subtract with v 1/3 x cubed times du, which is 1 over x dx. This simplifies to the negative integral of 1/3 x squared dx, which then we simplify as 1/9 x cubed plus c with the 1/3 x cubed ln of x. Let's take the integral of arc tangent of x dx, in which case we're going to now select the u substitution for the inverse. So we have an I and an A, and that's going to be u equal to the arc tangent of x, and therefore du is going to be equal to 1 over 1 plus x squared dx. dv, on the other hand, is going to be the times 1 in the original integrand, which is going to be dx, and therefore v is going to be equal to x. Now something surprising happens. So when we do uv, we get x arc tangent of x minus the integral of v, which is x, all over 1 plus x squared dx. And now this becomes u substitution, in which u is going to be set to the denominator 1 plus x squared. Du is going to be equal to 2x dx, but really we have this x dx, so therefore 1/2 du is going to be equal to x dx, in which case this integral now becomes the following. We have 1/2 the integral of 1 over u du, and we love that. That's going to be natural log. So therefore this becomes momentarily x arc tangent of x minus 1/2 natural log of u plus c, and we're going to then replace the u so that we get x arc tangent of x minus 1/2 natural log of whatever we set u equal to, which is going to be 1 plus x squared plus c. So why don't you guys give this problem a try? For right now, what I want you guys to do is attempt these problems. So this is problem A. Let's say we have 4x cosine of 3x integral dx. You will be using integration by parts for these ones. For B, it's the integral of 2 plus 5x times e to the 2x dx. Now be careful about this one, because you have this 2 plus 5x, you could actually rewrite this as 2e to the 2x, which requires no integration by parts, plus the integral of 5x e to the 2x dx, which does require integration by parts. For C, I'd like you to try the integral of arc sine of x dx.